Good morning, good afternoon, good evening, everyone. Thank you for joining us today at the CERAA 2024 International Conference on Control and Automation, Electronics, Robotics, the Internet of Things, and Artificial Intelligence. My name is Kezia Nathan, and I'm joined by my colleagues Javier Justin. The research that we have done is supervised and guided by our professor. They are Ivan Sebastian Edbert and Derwin Suhartono. We are from the Computer Science Department at Bina Nusantara University in Jakarta, Indonesia. Today, we are very excited to present our research on predictive modeling on caloric expenditure, exploring machine learning techniques for enhanced analysis. Our study explores the application of advanced machine learning methods to improve the accuracy of caloric expenditure predictions, a crucial component in health monitoring and fitness applications. So, this is the outline of our discussion today. First of all, we will start from the introduction. To set the context, let's first understand why predicting caloric expenditure is important. Calories, a measure of thermal energy, are essential for quantifying the energy we obtain from food and the energy we expend through physical activity. This knowledge is crucial for many people aiming to manage their weight and overall health. However, accurately predicting caloric expenditure remains a challenge due to individual differences in psychology and activities levels. Traditional methods like metabolic calculations or self-reported data often lack precision. In our study, we aim to address these limitations by applying several machine learning models to enhance the accuracy of these predictions. Our research begins with understanding the problem scale. As you can see, studies show that 27% of global consumers and 37% of people in the Middle East and North Africa are actively tracking their caloric intake. This number is expected to increase, driven by growing awareness of health and fitness. Given this trend, accurate predictions of caloric expenditure become increasingly vital, whether it's athletes optimizing their training, people managing chronic conditions, or the general population striving for a healthier lifestyle. The demand for reliable caloric expenditure data is clear. Next, we will discuss about the literature review. In our literature review, we explored previous studies on caloric predicting using various machine learning techniques. Different models such as like GBM, XGBoost, and neural networks have been evaluated across different datasets with varying results. For example, the large GBM model in some studies achieved a mean absolute error as low as 1.27, indicating high accuracy in specific contexts. Meanwhile, XGBoost and neural networks have shown superior performance in others, suggesting that model performance can be highly dependent on the data characteristic and the specific use case.
Now let's move to our methodology. The dataset used for the research is from Fmendes DAT253X demos from Kaggle. It consists of 15,000 rows of data. This dataset includes crucial attributes such as gender, age, height, weight, duration of exercise, heart rate, body temperature, and the actual calories burned. Here is the visualization of the dataset. As you can see here, we have gender, age, height, weight, duration, heart rate, body temp, and the actual calories burned, just like I mentioned before. Combining these attributes, our models aim to predict the number of calories expended accurately during exercise. This dataset's diversity in age, gender, and physical condition helps in creating a more generalized and robust model. Our research workflow began with data collection. We extracted the dataset from Kaggle, followed by preprocessing steps to clean and prepare the data for analysis. This included merging datasets, handling missing values, and eliminating outliers to ensure the data's integrity. Next, we perform feature engineering to identify the most influential factors on caloric expenditure, such as exercise duration, heart rate, and body temperature. We then split the data into training and testing to evaluate modules' performance, dedicating 80% of the data to training and 20% of the data for testing. And then we train the model with the dataset that has been prepared. Now, let's move on to result and discussion. Here, we present a detailed comparison of the models in terms of the different evaluation metrics. The XGBoost here model had a mean absolute error of 8.4943 and mean squared error of 159.6425 and root mean squared error of 12.6350 and an error squared score of 0.96.3, outperforming all other models. This model's accuracy highlights its sustainability for complex prediction tests such as caloric expenditure, where multiple interaction factors needs to be considered. Other models used are gradient boosting, linear regression, random forest, AdaBoost, extra trees regressor, and stacking regressor. Here is a visualization of the actual values versus the predicted value. As we can see here, the more compact it is and the more it is more straight to the line, the more it is connected more to the line, it shows that the model is more accurate than the other. As you can see here, the XG boost here is really thin to the line, really compact to the line. And if you compare it to the one like extra trees and random forest, it will spread out to the line more. This model comparison table shows that XGBoost is the best model used for predicting calorie expenditure in this research. Next, we will be giving our conclusion for this research. In conclusion, our study found that the XGBoost model offers the most reliable and accurate predictions for predicting calories burned during exercise among the models tested. Its excellent performance across all key metrics confirmed its potential for practical applications in health monitoring and fitness. However, it is important to note the limitations for our study. The dataset used, while comprehensive, is still relatively small and lacks diversity in some aspects. Future research could benefit from using larger datasets with more varied attributes to enhance the model's performance. Moving forward, we suggest several steps to address these limitations. Firstly, using larger and more diverse datasets could help improve the model accuracy. Secondly, exploring hybrid models that combine XGBoost with other techniques may offer further improvements in prediction accuracy. Thank you for your attention. We hope this presentation about calories burn prediction during exercise has provided valuable insights for everyone here that is attending and listening. Thanks again and stay healthy.